Elliston Corporation. In her role, Lorena provides technical support to a variety of projects nationwide, focusing on concrete and material technologies. In the last few years, Lorena has been at the forefront of understanding innovations in low carbon concrete and finding viable ways of incorporating it into construction practices. She is an active member of the American Concrete Institute and continues to work on advancing standards through both ACI and CSA. Without further ado, I introduce Lorena and turn it over to you for your presentation. Thank you.
Thank you. Can you guys hear me?
Yes.
Okay. I have to share my screen.
Yes.
Perfect. I think, can everybody see it? Yeah. Okay, great. Yeah, thank you for the great introduction. I'm going to be talking about low carbon concrete, and I'm going to describe what was done in the Eglinton LRT project to achieve carbon reductions. So I'm going to start the presentation by briefly talking about the department that I work for. Construction Sciences is an internal technical resource team that's available to help all of Elliston's projects. So as you can see, there are 5 groups in the department. Specifically, I work in the group called Building and Material Sciences, where we have team members that specialize in various topics, including mass timber, building envelope, modular construction, and concrete. So we'll start off the presentation talking about concrete and the ways that we can achieve concrete with lower carbon emissions. So just as a quick refresh, concrete is a material that's made by mixing cement, water, sand, coarse aggregates, and various admixtures. And out of those materials, cement comprises up to 85% of the concrete's carbon footprint. So we feel that it's important to dive into this a little bit more to help review the potential ways to decarbonize it. So where does carbon come from when we're talking about cement manufacturing? Actually, about 50% of the emissions are classified as process emissions. And so many chemical reactions take place in the cement manufacturing process. And one of the raw materials used to make cement actually breaks down and releases CO2 as a byproduct. Next come thermal emissions, so about 40%. And these are the emissions generated from the burning of fuels used to create the heat necessary for the production of cement. Over recent years, many of the cement plants in North America have actually been working on switching to lower carbon fuels. And so there's been a significant improvement on the fuel consumption and the efficiency of cement manufacturing. And that research is ongoing. Pretty much all the cement manufacturers are working towards that. The last piece of the puzzle is the remaining approximately 10% of the emissions, and those are attributed to everything else. That includes, yes? Sorry?
Yes, I'm sorry. I'm not seeing your presentation. I'm not sure if I'm the. I want to make sure that everybody can see you.
It's coming out in the middle.
You may have to pin it. If
yeah,
I'm not sure why that would have happened.
Andrew, just pin it on the screen, and then it should be fine.
Yeah.
I don't know if I can pin it. Does that work?
It should be fine.
Oh.
It's coming out.
Okay, so am I presenting still?
Yep.
Okay. Yep. So yeah, that last 10% is everything from the raw materials, transportation, preparation, and grinding of the clinker. So just to confirm, the screen switch to the next slide?
Yep.
Okay.
Yes, it did. Thank you.
Okay, so yeah, when we talk about low carbon concrete, it's important to note that the overall strategy is to create that balance between maximizing the reduction of the carbon impact of the project while we maintain the concrete performance. So we need to keep the strength, durability, and workability top of mind when talking about low carbon concrete options. So as we go through the presentation, we chose a benchmark concrete mix design, which we'll be able to compare everything to later on. We got this carbon emissions value for the 35 MPa air and train mix from the Concrete Canada's industry-wide environmental product declaration. And another way that you may hear people referring to carbon emissions is to say global warming potential values, or GWP values. Keep in mind that for higher strength mixes, this GWP value is typically higher, and for lower strength mixes, this value would be lower, and that's just relates back to the cement content in the mix. So let's get talking about some of the carbon reduction strategies. All the strategies available can be grouped into these three main buckets: cement reduction, which is basically just use less cement; structure and construction considerations, which is optimizing the design and the concrete mixes for carbon reductions; and the last bucket is carbon sequestration, which is capturing the carbon at the source. So the first option to reduce the amount of cement being used is to look at options such as switching to Portland limestone cement or alternative cementitious materials, which come with lower carbon footprints. And I'll describe more about those now. Portland limestone cement is also referred to sometimes as PLC cement or GUL cement in Canada. And it's a cement that's manufactured at the plant with a higher percentage of limestone compared to your typical general use cement. Typical general use cement is made in Canada with a max 5% limestone content. And this limestone content is increased to 15% limestone in PLC cement. So what does that actually mean? This increase in limestone from 5% to 15% equates to a 10% carbon emission reduction. The concrete industry in Canada is moving towards carrying PLC exclusively. So the main suppliers in Toronto, Vancouver, Ottawa, Montreal, they've all made the switch to this as their main cement type. So if it's already available at the plant, there's no cost premiums associated with its use. But we've also seen that there's been a lot of research done, and there's minimal to no impact on the performance of concrete mixes that use PLC versus general use cement for typical strengths. However, when we talk about those specialty high performance mixes, such as high strength mixes or shotcrete, there's limited data with the use of PLC cement, and that's when we start talking about the need to do additional testing upfront. As we just saw, like the cement content is the biggest contributor to the carbon emissions in a concrete mix. So the next method we're going to talk about is just swapping out some of that cement for other materials that will help reduce the carbon intensity of the concrete. These materials are typically, they're called supplementary cementitious materials, or typically referred to as SCMs. A typical concrete mix contains about 15 to 25% SCM already. And the most commonly used SCM types in Canada are slag, which is a byproduct of the production of steel; fly ash is a byproduct of coal combustion; and silica fume, which is a byproduct of the silicon metal alloy production. Silica fume is an extremely fine powder that's only most commonly used in high strength mixes and high performance mixes. So the opportunity for significant carbon reductions comes when we use these materials at higher volumes than typical. So we're talking 50 to 70% SCM content. Employing high volume of SCMs, or sometimes we refer to these mixes as HVSCM mixes, not only results in more durable concrete that is less susceptible to temperature-driven compromise during hydration due to temperature differentials, but it also significantly has benefits in terms of sustainability. And that's something we'll talk about when we get to the Eglinton LRT case study. However, these higher volumes of SCMs can lead to longer curing times and delayed strength gains. And so that's a challenge that needs to be discussed up front with the construction team and the designers. The availability of these materials varies by region and supplier actually as well. The fly ash is most common in Western Canada and Atlantic Canada. Slag is common in Ontario and Quebec, and silica fume is available nationally through blended cements used in high strength mixes. We really want to stress that the low carbon mixes that are currently being marketed by the concrete suppliers they're actually not doing anything fancy. They're incorporating a mix of PLC and SCMs at different volumes. And sometimes that comes with a cost premium associated with these mixes due to them being marketed as low carbon or low heat mixes. We reached out to 3 main suppliers in the Vancouver area to get some baseline ideas on cost and GWP values for the different options. So this slide shows the options provided by the suppliers in terms of both cost and GWP in kind of one summary graph. As you can see, burnt ghost prices are the most affordable. However, they're limited to what they can achieve with their low carbon options. Lafarge's base mix is already low carbon if you compare that to the other suppliers' baseline mixes, and it's actually lower carbon than burnt ghost low carbon mix. Lafarge right now shows no cost premium between their low carbon concrete levels at this time, and so that's something that we expect may change as the product use increases. Ocean's EvoBuild Gold is the mix that actually provides us with the highest carbon reduction potential of all of the suppliers. And as mentioned in the last slide, when you get to the high level reductions, both Lafarge and Ocean had comments in their submission stating that there may be a need for additional curing or a requirement to leave the forms in place longer than typical, potentially leading to schedule impact. So that's something to keep in mind. The next methods we're going to talk about are the structure and concrete optimizations. So many designers are looking into ways to reduce the carbon emissions inherent in their designs. And this slide is taken from Intuitive's Low Carbon Now study, where they compared a typical residential building in Toronto, and they tried to come up with lower carbon alternatives. So the first option they looked at is changing the shear walls to wallums, and this equated to a 2% carbon reduction. And the alternative, which saw the biggest reduction, is changing the design to incorporate only columns. When we get to the actual construction phase of a project and the schedule comes into play, we often see a big demand for high early strength mixes. So there's various ways to achieve these high early strength, but what's typically done is the cement content is just bumped up and we end up with a higher strength than the structure actually needs, which comes with higher carbon emissions. So if we relate this back to our benchmark 35 MPa mix with a GWP value of 417 that I showed early, and we order a 35 MPa high early mix, the concrete supplier may just end up sending us their 55 MPa mix, which would have higher GWP values. It would be close to 500, as you can see here. And that throws our carbon reduction strategies basically out the window. Here's an example test report for a 35 MPa mix, which was not even requested to be high early. But you can see that we got, in the red circle there, 47 MPa at 7 days, and we averaged 53 MPa at 28 days. So we want to stress that it's important to work with the concrete suppliers to ensure they're not just bumping up their cement content. the concrete suppliers want to avoid getting into low strength issues on site because typically they're the ones blamed first. So it's easy for them to just over design and include more cement in their mix than the mix actually requires. The last bucket we're going to talk about is carbon sequestration, which is finding ways to capture the carbon emissions at the source. Carbon Cure is a company that's being marketed really well. They invented a technology that is set up at a concrete plant and injects CO2 into the concrete as it's being mixed at the plant. So they claim a 3 to 5% emission reductions due to a combination of cement reduction and carbon sequestration. The CO2 is purchased from companies such as Lind, I think it was formerly known as TRACCS, and Carbon Cure sets up their system to be incorporated into the ready mix process. Their ambition is to eventually use direct captured CO2 from processes such as cement manufacturing, for example, but the technology is not there yet. So right now they're purchasing the CO2 to be used in their system. It's important to note that you can achieve carbon reduction by combining some of these methods I've talked about. For example, you can have a project that's using Carbon Cure and also implement the use of higher volume SEMs with the use of Portland limestone cement. And in this case, the carbon reductions would just add up. Carbon capture and storage involves capturing CO2 emissions from flue gas streams. In this case, we would talk about cement manufacturing and storing them. A lot of research is being done about storing them underground. So this process is aimed at reducing the amount of emissions that enter the atmosphere in the first place, and it's being widely studied right now as a means to deal with carbon emissions from all sorts of manufacturing processes. Lafarge has a pilot project at their Richmond plant, and Lehigh is getting set up with a similar technology at their Edmonton cement plant. So we see this method more as an option, definitely in the coming years. So what's coming down the pipeline? There's a lot of research at this time to work towards the goal of producing carbon neutral concrete by 2050. That's the goal that the Concrete Association in Canada has set for themselves. So, and just in general, a lot of concrete suppliers globally. And there's many proprietary technologies that are being studied for that. So for example, a technology that relates to carbon sequestration is Blue Planet Aggregates. And they're a company looking to utilize the emissions captured at the source to create an aggregate that you'll be able to use in concrete. Another example is Carbon Upcycling, which is a company looking at ways to inject CO2 into various supplementary cementing materials. There is the potential to produce Portland limestone cement with higher volumes of limestone, up to 35%, which is something that's already being done in Europe, and it's maybe coming down the pipeline in North America. And then there is looking at other alternative SEMs other than the slag, fly ash, and silica fume that I talked about, such as bottom ash, metakaolin, or even ground glass. Other technology I wanted to highlight is carbocrete and carboclave, and they're looking at ways to reduce emissions in concrete block manufacturing. So just in general, there's a lot of research that's being done on this front. So yeah, that's a short summary on low carbon concrete and the currently available ways to achieve it. And we're going to dive into the Eglinton LRT project and discuss what kind of savings we were able to achieve in the project and why we were able to do that. So just as an overview of the project, I'm sure you guys may be more aware of it than me, but the Eglinton Crosstown LRT is a large-scale transit project for the Toronto area. The goal of the project is to provide fast, dependable, and comfortable transit that runs along Eglinton Avenue, and it's going to help reduce the traffic congestion. Upon completion of the project, the ECLRT will connect East and West Toronto via 25 stations along a dedicated route. Since January 2014, a joint venture team known as Crosslinks Transit Solutions, or CTS, comprised of Ellisdon, Acon, Dragados, and SNC-Lavalin, has been responsible for the project design and construction. So in addition to the significant greenhouse gas emission reductions that will come by taking the cars off the road and reducing the need for buses, there was an opportunity to further reduce these emissions during the construction process. So that's what I'll talk about now. As I mentioned, the project has many stations, and even though they were constructed differently, some were mined, some were cut and cover, some were interchange stations, or there was a couple portals, they all had one thing in common, and that's lots of mass concrete. There are many definitions of mass concrete, but for this project, anything typically having a minimum dimension equal to or greater than 1 meter was considered mass concrete. So we went into this project knowing that the majority of the pours were considered mass concrete. And what do we know about mass concrete? It tends to get really hot, and we combat that heat by reducing the amount of cement and increasing the amount of supplementary cementing materials. In our case, for this project, we used slag. So in turn, we're able to meet the maximum temperature limits that are specified for the project in order to minimize thermal cracking. But we also end up having huge sustainability benefits through the reduction of cement. So there was a lot of testing that had to be completed prior to getting the concrete mixes approved. We started off by measuring the maximum temperatures for both 50% and 70% slag mixes. And we found that in order to meet the temperature limits for the project, we had to use a 70% slag mix. So then for each of the 3 concrete suppliers that were working on the project, we had to perform all of these tests that are listed on the screen in order to prove out the structural durability and the thermal parameters of each of the mixes. So I have some photos of the process. There were many, many cylinders and beams cast. And we also cast some cylinders for heat simulated curing. We also had cast these 6 pretty big elements, 2 for each one of the suppliers, in order to get the adiabatic heat curve of the concrete mixes and be able to develop the thermal control plans. These thermal control plans were going to help the site team as construction progressed. So we've now learned that another method that also works is by casting a 1 meter by 1 meter by 1 meter heavily insulated cube, which takes up a lot less space than this. I have a photo. So you can see all of these cubes and the previous ones were instrumented with temperature monitoring equipment. So we had probes at different locations within the element, and that was so we could get the temperature numbers from the mixes. So these are the results for one supplier. The yellow line is the core of the cube, and the red line is the bottom of the cube. So it actually, you can see based on the lines that our cubes were actually really well insulated. The green line and the purple lines are the corner and top, but at the top location. So you can see the zigzag on those because we had the testing lab come in to take core. So they had to remove the lid from the cube, and they had to core the element at certain times. So the opening and closing of the box was what created those jumps in the graphs. But basically, the outcome of this was that with that 70% slag mix, we knew we were going to be well below a limit of 70 degrees maximum temperature. I'm not going to show you all of the results because there was way too many. but I'm just going to give you an idea. Here are the compressive strength results for some of the cylinders that were cast. As you can see, the 3 suppliers were able to meet the 35 MPa strength requirement. But the max temperature reached was really variable, which kind of ties back to what I said about optimizing mixed designs and making sure you're not over designing, and that ties back to the whole sustainability aspect. So we started this process for the approval of conventional concrete mixes in 2015 and 2016, and we were able to get the 70% slag mixes approved. As all of the test results that we did actually came back exceeding the requirements. But over the course of the project, it became evident that there was a need to get more mixes approved. So in 2017, we realized there was a bunch of highly congested areas in a number of these stations. So we had to redo the same trials with a high volume slag self-consolidating concrete mix. And then in 2018, there were some areas where it was very difficult to install the wall forms and A-frames and move those around. So we had to redo the trials with high volume slag shotcrete mixes. So the successful use of 70% slag was used in all of the mix types that I mentioned. I'm going to talk about shotcrete a little bit because doing high volume SEM shotcrete is something that isn't typically done in the industry. Since for shotcrete, we're worried about all of those requirements I showed, but shootability, and more importantly, its ability to stack in order to make sure that it's not going to slough off. It's very important. So once we narrowed down a mixed design that would work, the final step was to do a trial program that included all of those tests and an offsite full-scale mock-up. So this was done to pre-qualify the shotcrete company as well as the nozzlemen, approve the nozzlemen that were going to be able to work on the project. That's just then the photos of pre-shooting, and we had to then core through the 1.4 meter thick wall and analyze the cores per nozzleman to make sure there was no voids, and we had a coherent concrete structure. So what does that really mean in terms of environmental benefits? By using 70% SEM mixes, we were able to calculate that CTS was able to avoid nearly 130,000 tons of CO2 as compared to using a mix with no SEMs. So while all mass concrete mixes have some percentage of SEM to aid in the temperature control, the impact of increasing the volume to 70% is significant. Just for context, the emission reductions realized here are roughly the same magnitude as taking 28,000 cars off the road for a year. And that's it. I think there's some time for questions, but I wanted to highlight this report on the left. That's Concrete Ontario's guideline for specifying low carbon ready mix concrete in Ontario. And that was issued 2 days ago and released to the public earlier this week. And so we're hoping that this will provide a little bit more of a guideline. It's a 65-page document that is available for anyone to review. Thank you.
Lorena, thank you so much for the presentation. I'm astounded as the difference that you mentioned of the carbon emissions. So now it would be a good time for people who have questions. You can type them in or raise your hand and we'll call on you. Okay, I got a question here and a message. It says, what is the biggest challenge faced in the industry halting the adoption of low carbon concrete materials?
Yeah, thanks. Great question. We see that there's a lot of project documents that have very prescriptive requirements when it comes to concrete. And so if we have, some specifications are limiting the amount of supplementary cementing materials, or they request a specific amount of cement in the mixes. And so these prescriptive specifications are not encouraging innovation in mix design development. And so switching from prescriptive to performance would be very beneficial for the implementation of low carbon concrete right now. I think that's probably what comes to mind first.
That's good. Lorena, in your field, would you say that low carbon concrete is the most, the biggest render of saving emissions, in carbon emissions?
Yeah, so I think Ellis Dawn in general is doing a lot the last few years about understanding the embodied carbon of materials in construction. So we're we're doing a lot about understanding concrete specifically, but also steel, mass timber, and just the different stages of carbon, energy optimization and all of that. So there's opportunity for reduction probably in every single construction material that we see. There's a lot going on right now. I heard a statistic about like the need for low carbon materials, or like just people talking about it has increased like some ridiculous like 2,000% over the last couple of years. It's just people are definitely talking more about sustainability and lower carbon emission materials.
That's great. I have some questions here. Danish Chaudhry is asking, you mentioned schedule impact. What is the extra cure time versus the standard of 3 days in summer and 7 days in winter?
So when you have high volume SEMs, CSA 23.1 specifies that you need the longer curing time. So you need 7 days and the amount of time required to achieve 70% strength. So it changes as per the requirements in CSA, and that comes with the mixed designs that are classified as HVSEM, or high volume supplementary cementing material mixes.
Good, thank you. I have other questions here. I'm going to read them in order. If you have any questions, you may type them in. Mark is asking, is there any incentive or opportunity to utilize recycled aggregate, concrete or other? What is the barrier to prevent this, and what cost-saving opportunities are there?
Yeah, so a recycled aggregate is a pretty big topic as well right now. I think it's used widely in like road bases and backfill material, but it isn't used too much in structural applications, concrete, because there is a hesitation, I think, from the industry about potential deleterious materials that may be inherent in the old concrete that's been broken up into aggregates. And so I think that's definitely going to change in the coming years, because there's a lot of talk about using recycled aggregates. And so right now there's potential in maximizing it in the use of it in the areas I talked about, or in not, your high strength or high performance mixes. I'm not sure about cost savings that would come from that. I don't know much about the price differences between the aggregates, just the local aggregates we use now and the recycled aggregates, but I do see recycled aggregates as a big option. And there needs to be a lot of testing that's done up front to make sure the aggregate is approved to be used in concrete construction. But I see that definitely being something that increases in the next few years.
Perfect, thank you. And we have another question here from Derny. It says, any impact about the performances of those type concrete on the future, etc.?
Yeah, so there's a lot of research that has been done with high volume SEMs for these mass concrete applications, because we're limited to the temperature differentials, and so it's been widely used in a lot of civil projects. So there's a lot of proven historical records with that. Where it gets to be a little bit different is when we're talking about using a different new type of SEM into mixes, and there's probably some hesitation in that because we won't know like long-term effects. But slag, fly ash, silica fume, they have lots of historical research. They are used to improve workability in the mixes all the time. They decrease permeability of the concrete, which helps with, for example, chloride ingression prevention. And so they're beneficial to improving the concrete parameters, as well as they have the sustainability benefits that come from that as well.
That's great. Thank you. And I have one more question here that says, what advice would you give a project looking to achieve similar carbon reductions as the ones achieved in Eglinton LRT?
Yeah, so for that one, I think planning is the biggest advice. Proper planning. As you can see, some of these tests are like longer term tests, not years, but to get the 91-day concrete strength, you need 91 days plus the planning time to plan the testing regime, discuss what types of tests are needed. And so I think testing your local materials up front to see what kind of benefits you will be able to get. As I said, we use 70% slag, but that doesn't mean that in Vancouver you could use 70% fly ash. So you need to work with your local materials, understand what those materials are going to do to your concrete mix, and optimize your concrete mixes. So it takes time to plan, and it's very project specific based on the requirements, structural requirements you need, durability requirements. So I would say definitely have meetings as early as possible and put the need for sustainability as well up front. For this Eglinton LRT project, just to be perfectly transparent, our goal wasn't to reduce the carbon emissions specifically. It was to meet those thermal requirements. And so the benefit from that was that we got the sustainability benefits. But if you have a project where both of those goals are at top of mind, you can work towards meeting both the performance criteria and as well as the sustainability goals that you have.
Thank you. We have another question here. What would be the challenges of having precast in a controlled environment as opposed to cast in place?
Yeah, so if we're talking about like sustainability, with sustainability in mind, with precast, you have a lot more, from my understanding, is there's a lot of time dependent kind of things you have to keep in mind. Like the precast manufacturing process is very fast paced. So they, pour one day and strip the next day, so they can keep the process moving. And so, through the use of steam curing and stuff like that, they they're able to speed up the strength development process. But there's definitely some challenges because they want to maintain that schedule, and what I talked about with the need of the additional curing and potentially strength delays. There may be some issues with maintaining those sustainability benefits and maintaining your precast manufacturing process as well.
That's great. Yeah, certainly some things to think about when planning a project. Thank you. If anybody has any other questions, would like to hear them now. Lorena, this was incredibly informative and really taking a look at the work you've been doing. It's certainly enlightening. So thank you very much. Here's this people thanking you as well.
Thank you.
So we really appreciate your time and all your knowledge, and for you to make all this information available to us.
Yes, yeah, and so I think that this is being recorded, and I'll share my presentation as well, and you can reach out to me if you have any further questions.
Yes, I will share with our attendees your contact info and also the link to the report that that was created by Concord, Ontario.
Yes. Okay.
So that will be available to all of you. Thank you very much. And just for everybody here to know, we haven't set up exact dates for the next webinars, but we do have webinars coming up from Summit Infrastructure, from High Speed Rail Solutions, and we continue working with our TRACCS webinar series. If there is anyone who has a topic of interest, you can very well email us and let us know, and we will do our best to bring those conversations to the table. These are the conversations that need to happen. So thank you everybody for joining us, and be sure to have a great day, a great rest of your day. Again, thank you, Lorena, to you and your whole team at Ellis-Dunn.
Thank you.
Thank you.